Right. So we had been learning about sequence alignment. So before we move on to more algorithms in sequence alignment, we need to understand one thing. In Niederman-Wunsch and Smith-Waterman, we apply a certain match and mismatch score, right? So we apply this Sij, if you recall. Now we fixed these scores for Needleman-Wunsch illustration last time, but there's no reason to fix this. For example, I fixed this to +2 for the match and -1 for the mismatch. Now there's no reason to fix this score like a constant. The reason is following: you can have certain amino acid changes, for example, in protein sequence alignment. For example, you can have asparagine changing to aspartic acid. Okay, so they are still acidic, and you can have serine to threonine hydrophilic amino acid. So some of the biophysical properties are largely preserved. So these mutations would be accepted in the evolution. Arginine to, let's say, lysine positively charged. You can have maybe alanine to valine changes, right? And likewise, so you can think of leucine to isoleucine changes. These changes are preserving certain fundamental properties, biophysical properties of amino acids. So they can be accepted in the evolution. Not all the time, not all the positions, but more often these changes are accepted in the evolution. Think of a scenario if you have change which is actually changing the biophysical property as well as uh, geometrical properties of the amino acid. Glycine is a small amino acid. Now, if it changes to, let's say, leucine or isoleucine, there is a big change in the properties of glycine over here. So these changes would be forbidden in the evolution. They could be deleterious for the organism. And likewise, let's say you have tryptophan and tyrosine, which is changing to, let's say, to a positively charged amino acid. Right? So we know that these hydrophobic amino acids are buried inside more often, and now it's changing to positively charged amino acids. This could be deleterious. And likewise, right, the changes which are changing the biophysical properties of the amino acids could be deleterious and forbidden in the evolution. So now if in the alignment, if we have these changes coming up, my mismatch score, right, my Sij, when it is not matching, when the aligned amino acids are not same, then this should be, the penalty should be less here as compared to this scenario, right? So Sij here should be very, very low, more negative, and they should be slightly up, right? Of course, it is going to be highest for the perfect match, right? Isn't it? Now, the same may apply to um, DNA alignment, DNA sequence alignment. For example, uh, there are certain mutations which are uh, actually more abundant, and they are quite often allowed also as compared to certain others. For example, transitions, which means that same kind of amino acid, same kind of base is changing to, for example, cytosine might be changing to pyrimidine, so it's changed, let's say it's changing to thymine, and guanine is changing to adenine. So these are transitions. However, if there is a scenario where you have transversions, right? These changes are transversions, right? They are relatively rare, right? So in general, you may say that the changes are not, the difference is not significant between transitions and transversions, but still there are differences. So this would be given by these differences that we are talking about uh, for the relative substitutions of bases as well as amino acids can be captured in something called scoring matrices, which will give us this information that how much Sij value should I apply for a particular change in my sequence alignment. So this matrix will be just 2 by 2 in the case of DNA sequence. For example, this is going to be C T over here. Sorry, 4 by 4 AGCT and AGCT, right? You are going to have this 4 by 4 matrix where you put up your transitions and transversions values. Of course, going to be symmetrical, but it's not necessary that they are symmetrical because T to C may not be that often as compared to C to T, right? Right. So these values are going to be very, very high over here, right? And then C to T is allowed. So C to T could be higher than the, let's say C to G, right? So C to G, this is going to be lower. So you can capture these uh, transition probabilities over here in these matrices. So this really makes sense. The scoring matrix makes really sense when you come to protein sequences. So how do we derive it, and what are the options available for us in the sequence alignment? Right. So let's look at some of the scoring matrices. So uh, scoring matrices. So primarily there are two kind of scoring matrices. So one is uh, known as PAM and other is known as Blossom. Right. So the PAM stands for point accepted mutations. Blossom stands for block substitution matrix. So we will see what exactly do they contain. Okay, let's talk about PAM first. PAM. So PAM was given by Dehoff. She was also the first person to make the first protein database, which is now known as UniProt. Initially, it was documented in the book form, and then it was converted into an online database, which was later on popular as UniProt, which was having all the sequence and functional information of known protein sequences. So this was given in sometime in 1970s. Now PAM stands for point accepted mutation. Okay, mutations per 100 residues of a protein. Okay, per 100 residues. Accepted here point is of course it's a point mutation. The accepted stand for accepted means accepted in the evolution, right? So that's the fundamental definition, expansion of PAM abbreviation, point accepted mutation. Now, what was done in PAM? So the first thing that which was done was what Dehoff did was she collected certain sequences which were highly similar. All right. So These were around, if I recall, 71 sequences, protein sequences. Which were highly similar, right? So similar means they were having at least 85% sequence identity. Identity means exactly same amino acid, right? Similarity means they can have similar amino acids, may not be identical. So that's the difference between identity and similarity in bioinformatics. And they did the alignment of these highly similar amino acids, protein sequences. Now you might wonder, since for sequence alignment, so this is multiple sequence alignment. Since for any kind of alignment, we need scoring matrices. And in turn, we need alignment to get the scoring matrices. So this is like a closed loop to which came first. So actually in the beginning days, MSA was being performed manually. And since these sequences are very, very similar, aligning manually was not very, very challenging. And they took a very limited number of sequences. And in fact, the sequences available as in those times were very, very limited. Right. So now, of course, if you want such scoring matrix, you can apply the available algorithm for multiple sequence alignment. All right, so this is the fundamental thing, the starting point to get a matrix in PAM. Okay. So let us see what exactly was done. Okay, the first thing is that let us say you have these sequences over here which are aligned. Okay, roughly similar length, right? And you of course have changes over here. And since these are very highly similar sequences, these changes that I'm highlighting in amino acids will be rather fewer. Okay, so there are changes. These are some amino acids changes in sequence alignment, right? Now we have to count these changes. Which amino acids to which amino acid is changing? Okay, after counting this, you could get a matrix. Right? That will be your starting matrix. So you count how many alanine to glycine, how many asparagine to aspartic acid, and so on, right? And you could get a fundamental substitution matrix, amino acid substitution matrix, which will of course be the size of this would be 20 by 20, 20 amino acids, right? You have 20 amino acids by 20. So of course the diagonal here represents the no change in amino acid, right? So this and the non-diagonal entry, let's say there is one entry over here or certain amino acid to certain other amino acid, would represent the substitution, the number of changes from amino acid A to B, right? And this is telling you again A to B, but here the B is again A. So this is no change basically. Getting this would be easier from this alignment. One could get it. However, it turns out that to get this matrix in appropriate form, you need certain kind of scaling. Okay, this matrix needed scaling. Okay, so we actually need to put up the probability values, not the count values. Okay, so these are just the frequency, the counts, A to B changes and A to A changes and so on. So we do not want that. We actually want the probability values to fill in. So these are obtained in following manner. So let us say the probability that I want to calculate is what is the probability that A amino acid is changing to B. That will be the element of my matrix, scaled matrix. All right. Now here, this is basically a problem of joint probability, conditional probability basically. So there are two things here. First of all, the first thing is that what is the probability that A has changed, right? And what is the probability that A has changed to B, right? So this is some kind of joint probability here. So, and we know that the way we calculate it is following. Is we can say that what is the probability that A has changed, A is mutated, times, this is the fundamental conditional probability that you would have learned in your statistics class, and the times the probability that A has changed to B. This is the joint probability now, given that A has changed. Okay. Now you might say that this could be rather straightforward, but the scaling of PAM had other things also. So we will look into that. So the first thing is that, of course, the probability that P has changed number of times we see A has changed, right? So by the total number of mutations, right? How many times A is mutated in this matrix. In other words, this is nothing but sum over B basically for FAB, right? So this is my FA. All the changes over other amino acid which is given by B, and my F is basically sum of all FA. F is equal to F sum over A FA, right? All the mutations times probability of changing A to B is the number of times we see A has changed to B, FAB. This is the same FAB divided by number of times A is changing, right? Now you might cancel FA and all that, but there's important thing that the reason I'm not doing so is that this is not sufficient. This scaling is not sufficient. This scaling is actually not sufficient. In fact, this is actually expressed. You remember, I said in the previous slide that we have point accepted mutations per 100 amino acids, right? 100 residues. So this has to be scaled as per the definition of PAM. Okay, and the way we do is we defined a mutability, relative mutability of each amino acid. Okay, so I'll show you how this has to be scaled further to calculate mutability and expressed as mutability basically. Mutability ability of A, let's say MA, is given by see, of course, we have to take FA by F, total number of mutations involving A out of total mutations, right? And this has to be scaled by 1 by 100 times PA. Okay, PA is the probability of observing A. What is the frequency of A? Frequency probability of A. Probability of A in the sequence, right? We'll just count the number of A's divided by the length of the protein. Now you might wonder, why did we do so? 100, as you can guess, is coming because we want to calculate per 100 residues. Now here is the thing, if you want to understand this in little detail, what does this represents? This represents the number of amino acids, number of A's, number of A amino acid in 100 residues, right? So probability of observing A times 100 means number of, so this is basically number of A's in 100 residues, right? Okay, so what does the other part represent? So what does this represents? whole of this. This is 1 by number of A's in 100, so which means that it's telling the probability. This is basically probability of or probability that one of the A is mutant. Probability that one of A in 100 amino acids in 100 residues is mutated, right? So that's what we want to look at, right? So you might say, why did I bother about one while the original definition says point accepted mutations, which means that I can have more than one also. But I forgot to tell you one thing, that the first matrix that we are deriving here is actually not, it will only have 1% mutation, which means that one mutation per 100 residues, which means that the matrix that we are deriving right now is PAM 1 with 1% mutation, okay, per 100 amino acids. Remember, this is important. Right now, what we are doing is we are obtaining a matrix called PAM1, not a general PAM. So this is whatever we are doing here, we are doing it for PAM1, which means one stands for 1% mutation or number of mutations accepted in 100 residues, right? That's what this number means. So now we don't express this as FA by F, we simply write it as in a scale form. So this is going to be MA, mutability of A, times FAB by FA, right? So let us call this as M prime AB. So this is whatever we got here is this probability. Since we have already scaled here, so this was original one. So now since we have scaled this, we call it as MAB, which is derived from M prime AB, right? So this was part of your M prime AB. So just to simplify this now, instead of writing, so this has become a little bit confusing now. So let's just get rid of this prime thing. This is just MAB, right? So we actually express this in log form, log ratio, log 2 form, right? So what it actually represents is the following. FA is basically your expected value now, right? FAB is the value that A is mutating to B, and what should be the max value that A is mutating should be FA. So that's like a expected value. This largely becomes like a observed by expected log 2 ratio, which means that if you now get your matrix, now fill your matrix with these values. This should be filled up in this matrix. So you can get the negative score also. That would tell you that we have a positive means they are actually allowed, right? And negative means they are forbidden in the evolution. So this is PAM1, okay? So this is just the PAM1. So which means that we are just capturing 1% mutation. While what do we do for the sequences that we are aligning are diverged, then we cannot work with PAM1 because this is derived from highly similar sequences, right? So we need to move further from PAM1. So how do we get PAM2? So PAM1 was telling you that we had, so we were calculating MAB probability. And our assumption was in PAM1 was that uh, A is directly mutating to B. That's the assumption of Dayhoff, because we took very closely related sequences. They were having very high sequence similarity. So we were assuming that A is directly changing to B amino acids. It's not a multi-step process, it's just a one-step one. Now, if the sequences have diverged further, it means that there is no reason to believe that A is directly changing to B, which means that now A is changing to another amino acid X, and that has changed to B, right? Isn't it? So this is your PAM2 would capture this thing. So this was your PAM1 thing, this will capture your PAM2. Now, how do we actually calculate this? Now your MAB for PAM2 would become MAB would become M of changing A to X first, right? Times, this should be the joint probability, how often X is changing to B, right? Now there is, so this is 2, right? So this is PAM2, so I just put 2 there. Now this is, uh, now X can be 20 amino acid, right? So we have to sum this over X, right? This should go to 20. What exactly are we doing here? In whole of this, what are we doing? This is nothing but, this whole thing here is nothing but matrix multiplication, right? Matrix multiplication. So what do you do in matrix multiplication? When you square a matrix, when you square M, when you are squaring it, M times M, you do this thing, right? So you take column and the rows and you get the uh, product and then sum it over, right? That's what we do. So this is nothing but the matrix multiplication, which means that if I have PAM1, I can get PAM2. So my PAM2 would be my PAM2. If M is my PAM1, my PAM1 is M matrix, then my PAM2, okay, then my PAM2 would be M square, right? Now what will be PAM3 then? PAM3 is going to be M square times M, right? So this is going to be M3, M cube, right? This is my PAM3. And likewise, we can get PAM4 and so on, right? So in each of these iterations, in each of these multiplications, we are actually diverging in sequence. Sequence divergence, right? So if this number is smaller, it means that we are looking at highly similar sequences. If this number goes less up to 250, then it means the sequences are very diverged. 250 mutations per 100 residues. Now you might say that how is that possible? It is possible. The same amino acids uh, can change further, right? So there could be multiple mutations at the same site. So theoretically, it is possible. So, uh, which means that the PAM has a unique feature, and that is it is extrapolated, right? So this divergence, PAM1 is obtained, PAM1 is observation. So this is your observation. It is obtained from your observation by aligning similar sequences, right? This is but these PAMs are extrapolation of PAM1, which keeps the this is also making assumption that mutations are independent from each other. This is also telling one thing. Of course, this is making the things simpler for us. We don't have to align more sequences to get PAM4, PAM100, PAM250. At the same time, there is a drawback, and that is if we get some error in the beginning, it will be amplified through extrapolation. So this is PAM. So there are other matrices which are actually based on solely based on the observation. There is no extrapolation. So that one of those matrices is known as Blossom. which stands for block substitution matrix. This is given by Stephen Henikoff in 1980s. Right. So what they have done, they have taken around 2000 groups, different groups of sequences of protein sequences, and each they were varying in their sequence identity. For example, some of them were 45% identical, 62% identical, 85% identical, and so on. Okay, they made different groups which were varying in their sequence identity. You can have, so there is a more divergence over here and less divergence over here. So then if you get the numbers of blossom, okay, so there would be a number also attached with blossom, just like PAM. So you have blossom, if blossom 45 and then blossom 62, blossom 85, and so on, right? If this number is increasing, it means there is a more similarity, okay, similar sequences, and more divergence over. This is inverse of what you saw in PAM matrix. Now this cannot go more than 100. So in PAM you can go up to 250 or whatever. There's no limit. But here you cannot go more than 100 because this is percentage identity over here. But the direction is inverse. If the higher the number, more similar the sequences are. In PAM, higher the number, more diverse the sequences are. Right. Now again the same thing that we did in PAM. So what we do, let us say you have these sequences S1, S2, S3, and so on. And let's say the sequence was BAA. This is protein sequence, small protein sequence. Second sequence was BBB. You have aligned them, and CAB. So what you do is find out how many times B is converted to B, which means there is no change. A is converted to B, A is converted to B, B is converted to A, and so on. B is converted to B, B is converted to C, and so on. You count these instances, and then you make a table where you write these observed counts of, let's say, how many BB were there, how many AB were there, and so on, how many AA were there, and so on. And you write your observed counts, and let us say the observed count is, in this case, how many BB? 1 and 2. 2 BB were there. So I write 2 over here. How many AB? This one is 1. 1, and then 1, 2, and 3. Let's say the mutations are symmetrical, whether A to B or B to A, or let's say just two. Let's not confuse. Okay, just two of them is A to B, and then you calculate the expected value, right? This is rather straightforward. It's just the first step of PAM, right? So you calculate how many times B comes along with B. What is the theoretical expected value? That should be the joint probability of number of B's times, or probability of B times probability of B, right? So this should be divided by the length, right? How many BB were there, and so on. And sorry, so this should be divided by the alignment length, which means 1, 2, 3, 4, 5, 6, 7, 8, 9. So this should actually be divided by. So let me finish this first. This should be divided by, let's say this will be, so now if I put P here, probability, this is going to be 2 by 9, 2 by 9. And what will be the expected one? Expected one will be P of B plus times P of B, right? This is joint distribution. You're going to get how many P's were there? B were there 1, 2, 3, 4, 5. 5 by 9 times 5 by 9. And likewise here, how many A were there? 1, 2, 3. 3 by 9 times 3 by 9. So you got the observed values and the expected values, right? So you make a matrix of this. You got the log 2 of observed by expected, and you make a matrix that is your blossom matrix. This is rather straightforward, right? Okay, so let's quickly look at what are the differences between PAM and blossom. Okay, PAM, blossom. One thing I forgot to mention in blossom is that these are when we obtain these uh, group these sequences, we actually looked at the blocks, not the complete sequences, small chunks of sequences which are similar. Okay, that's what the block stands for here, which means that we, if this was the whole sequence, we only look for the sequences which are highly conserved, the blocks, right? Not the whole one, right? So this statistics is actually obtained for these blocks only, right? So the first thing is that the first difference would be between PAM and Blossom is the how they are derived, right? So well, you could say that this is extrapolated one. This is observed. Extrapolated because PAM1 is never used practically. You use higher PAMs, right? So those are actually extrapolated. So you actually, this is more suited for the global alignment thing because the metrics are derived from end-to-end alignment. So this is obtained for blocks only. So it is better suited for local alignment because of the sheer reason, because of the origin of these matrices. So higher PAM, higher order PAM means divergence. This is higher order blossom means similarity. These are the fundamental differences between PAM and the blossom. All right. All right. So let's move on now with the sequence alignment algorithm. We'll talk about BLAST now. I have mentioned the BLAST, and some of you have actually done the BLAST in one of the assignment. So we'll see how does BLAST work. Let's look at the algorithm first. Okay, so we'll learn about BLAST, basic local alignment and search tool. This is given by Alshul in 1990s. This was one of the fundamental, one of the path-breaking technique method, which has changed the way we look at the sequence alignment. So as I mentioned in one of the class that we are actually, let us say you have an objective, you have one small sequence with you and you want to check out where does it match to the whole database that we have. Database of millions of sequences, right? You have millions of sequences in different databases, right? So where does it match to? If you want to find out where does it match to, you have to do BLAST, right? So this is one too many. You can't do the brute force search. It's going to take humongous amount of time. It's going to be an NP hard problem. So you need to do it using a heuristic approach, and one of those is known as BLAS. Okay, so let us look at how does it work. The first thing is that, let us say this is your sequence, query sequence. This is your query sequence. The first thing that you do, you make based on a word length, you make a library of words. So this is the way you make a library. You take all the sliding windows across this query sequence, right? So then you expand this library. So you have, so the word length, so let us say the word length W is 3 here. Okay, this word length should be longer for the DNA sequences because you only have 4 base pair, you need sufficient complexity. For amino acids sequences, the word length of 2 or 3 is sufficient. Okay. And then you expand this library, and the way you expand is following. That's why we learned about PAM and BLOSSOM. We get the neighboring words now. For example, let us say you had one word name as RDG, is arginine, aspartic acid, and a glycine. Now you will get the neighboring word of RDG. The way you get it is you score another word which is similar to this one. Let us say aspartic acid, asparagine, or NG. You score this one, or EG, okay, glutamic acid, and so on, okay. And then you keep on diverging. Now, how do I know that these are more similar to these sequences than, let us say, somewhere I had alanine, 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 which is very, very different? That's because you can score them, right? How do you score them? Arginine to arginine would be very high value, right? So this is going to be, let's say, some value 0.99. It's not changing. D2N is, let's say, 0.7. From your substitution matrix, glycine to glycine is again 0.99 or so. These are some arbitrary values just to show the difference. So you add them up. So you add them up and you get a score for this sequence, right? And likewise, and you sort them based on this score. So that will be your neighboring words. All right, so from this 0.99, I recall one thing which I forgot to mention in the PAM matrices. In the PAM matrix, you make sure that your sum of MAB should be 1, which means that each row is summing up to 1, right? In this one. So which means, so if I say sum when A is not equal to B, which means diagonal ones, then this has to be 1 by 100 because this is PAM1. So 1 by 100 is 0.01, right? For the non-diagonal one. For the diagonal one, it should be MAA should be sum over MAB, all the values of each row, right? So each row means I'm talking about B over here, okay? 1 minus this value, 1 minus this value, which means that it has to be 0.99, right? So so this is before taking the log ratio. This is before taking the log ratio. Your diagonal values needs to be 0.99 and your non-diagonal values should sum up for each row. So each of these are 0.99 in PAM1 and each of the row sum would be 0.1 for the non-diagonal one. Let us say from here till here, right? Yeah, so non-diagonal one. That should sum up to, non-diagonal one should sum up to 0.01, sorry, 0.1. I forgot to mention this. When I typed 0.99 over here, I could recall. Nevertheless, so the idea is that you get these neighboring words and score them based on the scores that you can get from substitution matrix. So you score them and you stop somewhere. Let's say you had arginine over here, and then RGG, and then it became GG. It is diverging, GAA, and so on. You stop somewhere, after which is, let us say, score drops. These scores that we are calculating over here, scores are dropping drastically after this. So you stop and do not take these ones. Okay, and this is your library of neighboring words. Library of words. Words plus neighboring words. This is your starting point. Once you get these words, you throw them onto a database, okay, or to your subject database, whatever was your database. You have all the sequences over here. This is full of sequences, right? So you take these words, let us say you took RDG, and you throw it over this database and find out where does it match to. So you have to do it for each one of them, right? So once you have done it, let us say you find a hit somewhere. Let us say over here. Let us say over here you found a hit. Okay, so, and this is the next step now. Let us say your word was RDG, and it found a sequence RDG over here. That's the perfect alignment. The second step is now once you get a hit, you start expanding on either side. Okay, look here, what is out there. I'm looking in the neighborhood now. I found that there was alanine here. There was alanine here. Right. And when you look at your query sequence where the RDG was, let's say it was here, what was the neighboring sequence? Okay, neighboring amino acid, and you found alanine there. So you got a match, and then you found that there was arginine again over here, but you find lysine. So there was some imperfect match. It can still be allowed in the evolution. And then you found, let's say, serine here and threonine here, and so on. But after a while, you observe that, and the same way on this side, let's say you had D here and E here, and you said there's some similarity. But after a while, so this was scoring well because these are accepted kind of mutations. So this alignment is working really well. Now, what has happened after that? I found that there was a glycine here, and I found leucine over here, and let's say serine here and tyrosine here, which are not aligning well because their score will be very low. If I look at my, let us say I look at my blossom matrix and I see how often G is converting to leucine, this will be in negative, right? These are not actually allowed in the evolution. And likewise here, there was a, let's say, alanine here, and which is now changing to charged amino acid R, okay? And so, which means that if I start looking at score, what was the score when I aligned these three only, okay? And what was the score when I moved from here to here? And what was the score when I moved to here, and so on, right? I'm only plotting it for one side, right? So then what you do is the following: you plot this score, okay? You plot this score as a function of gap extension on this axis, extension by 1, 2, 3, 4, 10, 20, whatever, and the score on the y-axis alignment score, how it is changing. So you have one extension, 2, 3, 4, 5, and let's say the initial score of RDG was somewhere here, and then we observe that the score is actually increasing, and then it suddenly started decreasing, right? So you stop when the score is decreasing after certain threshold. Okay, these thresholds can be predefined in the algorithm. Okay, so this extension will continue and will stop when the score is dropping somewhere. So let us say in this case, I stopped here and here and reported this as my alignment, right? My blast sheet. And you do it for all the words. So this is the way it reports, the blast reports the small chunks of local alignments. Now for these are called HSPs, high scoring fragments, right? So now here each one of them will give you one final score, which will be here, right? Now Alshul has used these scores to calculate E value that you will see in each blast implementation. E value, which is given by following equation. There is some constant K, the length of the subject query. What was the subject query? This is your subject query over here. What is the length of that? What is the length of query? So this is for subject. This is for query sequence. What is the length? E raised to the power minus lambda times S. S is your alignment score. Now lambda is a constant given by Alshul factor. It's known as Alshul factor by the author name. And I can briefly tell you what exactly it is. It's basically a scaling exponent, which tells you that how the score of knowns, what is the distribution of score values across, let's say, certain database. If you align the, let's say that you have some query data set, and then you align against a database, a lot of similarities. So you take all these aligned fragments, right? These are aligned fragments, and calculate their S and look at what is their distribution. It turns out to be distribution would be actually somewhat like power law or a fat tail distribution, S and number. So this lambda tells how quickly this distribution is decreasing, which means that if you plot this distribution in log scale, it will be inverse line S times number. What is the slope of this line? That will be given by lambda. Okay. So it is clear that if you have, I just gave you brief description what is lambda here, but this is known as Alshul's constant. So S is, if scoring, if the score is high, E value will be very, very low, which means lower the E value, better it is. And if your query sequences and the subject sequences are longer, E value would be poorer, it will be larger. Okay, which means that if you have shorter sequence and you are doing blast as compared to your longer sequence, and you are doing blast of these two sequences against database, and you need your E value would be larger for this sequence. So if there is an option on a blast implementation in NCBI to report the alignments which are having certain E value cutoff, that only report below this E value. Okay, because it can't report all the searches, you will not have much space on your browser. Let's say if it is, let's say 0.01 for longer sequence, right? That could be fine. That's the cutoff. It will show results up to this value, E value, not greater than this. Okay, if it is greater than the 0.01, it will not report because these are poor hits. But at the same time, if you have a shorter sequence like your primer sequence, okay, you need to have a value which is much lower, let's say 0.01, something like this, or 0.001. Okay, 0.001. So longer the sequence, E value cutoff should be adjusted accordingly. And lower the E value, it tells you that what is the random chance, that what is the chance that you will get this sequence hit by chance, randomly, right? So this is what the E value signify, and this is the equation. Now, before BLAST, there was another algorithm which was proposed and which is not very popular now, and that's known as FASTA. FASTA stands for fast approximation. A stands for approximation. Now, it's very similar to BLAST. However, it's not as smart as BLAST. What you do is the following. Let us say this is again your query. You again get the words that they call as k-tuples, same as words, right? So these words are again thrown to a database, and let's say I'm making a dot plot against the database. This is my subject, and this is my query on this axis. Okay, in my dot plot, I will find some diagonal hits, right? And so on. Because database is huge, there could be a lot of hits. What it does is it will apply certain threshold. It will apply certain threshold and say that above, if the scoring of these diagonals, score of these diagonals, the alignment score of these diagonals is above certain threshold, I will only consider that. And let us say that what it found was all this is noise. These dots are all noise. The real alignment is, real hits are these three over here and these two. Okay, and rest all is just noise. So then what do we do? If I already uh, uh, apply the cutoff and I got this result, the next step is you take this diagonal and apply Smith-Waterman, because now you would say that I need to fill up the, where is the extension? So these are small words. You remember, these are small words which are aligned together, and then there was a gap. Right. Now you might say that what is the parallel to extension that we did in the BLAST? You remember we did the extension in BLAST. So this is the extension that we were doing over here, right? Now the thing is that you might think that where are the gaps in BLAST? BLAST is essentially originally is ungapped. Now we have a gapped version also, where you, once you insert a gap, you put the gap penalty in your score, as you do in other alignment algorithms. In FASTA, what you do is you apply, after you identify uh, the regions, the diagonals which are actually having high score, you fill up these gaps by applying Smith-Waterman algorithm, right? So basically, you're going to Smith-Waterman will also optimize some of this. May insert small gap over here also, right? It will also optimize the alignment. So you fill up these gaps based on Smith-Waterman algorithm. So the extension part is done. Extension plus refinement by Smith-Waterman algorithm. So where are we saving space? Where are we saving the calculations? Now we don't have to do this Smith-Waterman across all the subject queries, subject sequences. We only look for the regions which are showing uh, very high scoring diagonals, right? So this is what the FASTA algorithm. All right. So in the next class, so we will stop here, and in the next class we will learn about the multiple sequence alignment and the profile. How do we get profile, HMM profile for multiple sequence alignment, and where do we use it?